afternoon. Yes, it's afternoon. Good afternoon, class. I hope you're all fine. I can see now we are 23 of us. So we will start, and I believe the others will join us as we continue. So I think, class, hope we summarized. That's my hope. I hope we summarized on the H1 blockers. If we did not, please inform me of the same if we did not. And if we did, now we start on still on the antihistamines. Remember, we did mention we have the H1 blockers and we have the H2 blockers. So what we are looking at are what we call the classical antihistamines. The classical antihistamines are those that block, or those that are used for allergy. Those are the ones that we call the classical antihistamines, and they were the ones we were looking at. Now we want to look at the other class. We normally don't call them antihistamines. We actually just call them H2. They aren't actually antihistamines, but basically when somebody talks about an antihistamine, you think of the anti-allergy agents. So these H2 blockers are also antihistamines because they block the H2 receptor, which is also a histamine receptor, of course, to bring completely different effects. So histamine is able to bind two receptors. For one of the receptors, it will bind to release to bring about allergic reactions, and of course increased permeability and therefore edema and so on. For the other one, it will bind the H2 receptors. Once it binds the H2 receptors, it will bring increased gastric secretion within the stomach, and therefore it will enhance ulcers, or it will precipitate ulcers. So those are the very different receptors, two of the most important, very different receptors. Of course, you have H3 and you have the H4, but the most important are H1 and H2. So we are now going to look at the H2 blockers. These ones specifically go for the H2 receptors, and you will see, yes, they will have some structural resemblance to the histamine. They do have structural resemblance to the histamine, but at the same time, they do have some structural differences so that they can go and bind the H2 receptors. When we look at the H1 receptors also, we did mention there's some structural resemblance in that in the H1 receptors, of course, in place of the imidazole ring, which is a bit smaller, you have bulkier rings. In place of the imidazole ring, you have bulkier rings where either we had a phenyl ring, in some of the areas we had a pyridyl ring, in some of the areas we had a benzyl ring, and even in some of the drugs, in somewhere we did have the zonzil ring and so on. So those rings, those bulky rings within the H1 antagonists actually replacing the imidazole ring, which is much smaller. Then again, if you look at the histamine, it does have also a spacer. The spacer is usually two atoms, the two carbon atoms, the CH2. So it also has a spacer. It also has a protonable nitrogen. So when you look at the H1 blockers, for sure there was a spacer. It could be a 3-carbon atom, it could be a 2-carbon atom with retention of activity. Then, of course, also the H1 blockers also had a terminal nitrogen. And if you look at histamine, it also has a terminal nitrogen. So although those structures of the H1 blockers and the histamine, by looking at them, they look very different. But when you scrutinize them, you will see there is indeed some structural resemblance. But of course, the H1 blocker is a more bulkier drug. It's a more bulkier drug because remember we said it binds the receptor at the protonable nitrogen, and then the bulky groups kind of bind outside the main receptor, and that's where we say it looks like there is stereochemistry outside the main receptor. So there is structural resemblance, but you require a bulkier molecule which will go for the receptor, bind it more strongly, do not really have agonist activity, and therefore once it binds, it does not trigger any pharmacological activity. It blocks the receptor and therefore is responsible for antagonist activity. When we look at the H2 receptor H2 blockers, we also expect to see structural resemblance between. Just one little minute. Sorry about that. So we were looking, just as a brief, that as an introduction rather, that even for the H2 blockers, we do expect structural resemblance. We do expect that these drugs will resemble histamine, again have structural resemblance, and also have some structural differences, and even sometimes some different characteristics, so that again these drugs will not go for the H1 receptors, they will specifically go for the H2 receptor. And when they go for the H2 receptor, again they are not agonists, they will not trigger that receptor, but they will block that receptor. They will block that receptor. And as we have said, these drugs are anti-ulcer drugs. So when they block the receptor, what they are trying to block is the release of gastric acid or hydrochloric acid, because hydrochloric acid is the one that triggers ulceration. So that, in a nutshell, is what we expect. So let us now move on. So we are saying introduction, what are peptic ulcers? Peptic ulcer is a localized erosion of the mucous membrane of the stomach, and the pain is caused by irritation of the exposed surface by stomach acid. In other words, it is an ulcer. It is a wound. A peptic ulcer is just a wound. It is where there is ulceration. The mucous membrane has been eaten away, and therefore there is a wound. So that wound, when it comes into contact with hydrochloric acid, it will cause a lot of pain. And that is why for those who have ulcers, ulcers are very, very painful. So what we are trying to do for such people is now to reduce the HCl, or you reduce the HCl, and at the same time you can trigger excess production of mucus, or production of something like sodium bicarbonate that can neutralize the acid around. So one of them is block the release of HCl. In addition, you can produce also mucus, which can coat this ulcer. Number 3, you can also trigger production of sodium bicarbonate that can neutralize the acid around the wound, and therefore stop the irritation, because we are saying the major problem is when that wound, when that ulcer comes into contact and HCl, being at pH about 1 to 2, irritates that wound and has causing a lot of pain. Secretion of gastric acid occurs at the level of the parietal cells. I believe you have done this, even if it's in first or second year. You talked about, you must have done this in medical physiology or in pharmacology, in the parietal cells. And the parietal cells are also known as onxentic cells. So parietal cells of the onxentic gland. So they're also known as onxentic cells in the gastric mucosa. The secretory process occurs via what we call the hydrogen potassium ATPase pump. In other words, when you have that hydrogen potassium ATPase pump, that means it's an active transport. So this secretory process occurs via hydrogen potassium ATPase that exchanges hydronium ions with uptake of potassium. Remember, you must have a balance of charge. There must be a balance of charge. So the ATPase means that even if the concentration of the hydronium ions is slightly low within the parietal cells, onxentic cell, it will be pushed out through this, which we are calling an active transport. Active transport works even against concentration gradient. And for the charge balance, when you push one hydronium ion out, the charge within the mucosa, within the gastric mucosa, will be much higher with one positive. So therefore, a potassium ion must move back to replace the hydronium ion for us to have a balance of the charge. Otherwise, you will start conducting electricity in your body. So that's what we are talking about, an exchange of hydronium ion with potassium ions, of course, both of them carrying a positive charge, and therefore the balance of the charge is very straightforward. Several mediators that regulate this secretion by way of receptor system on the basolateral membrane, there are several of them. You, of course, have the H2 histaminergic pathway, which is cyclic AMP dependent. And then you also have gastrin. You've definitely mentioned gastrin. You have muscarinic receptors, which are triggered by acetylcholine. So gastrin, muscarinic, acetylcholine, histamine can trigger this release of of hydrogen or hydrochloric acid. So receptors also regulate the secretion of gastric acid. Remember, the gastric acid is a HCl through calcium ion dependent pathways. The other one is cyclic AMP. So we are only saying different ways can trigger the release this HCl. But when we give these drugs, at least they will block one pathway, which is a histaminergic or H2 cyclic AMP dependent pathway. Then the prostaglandin effect, we've already looked at prostaglandins, and we're just reminding ourselves that also in parietal cells, the E series prostaglandins work in opposition to the histaminergic pathway, inhibiting histamine-stimulated adenyl cyclase activity. So the prostaglandins will inhibit. Remember, the histamine is acting through cyclic AMP. The prostaglandin will inhibit this the adenyl cyclase activity, and therefore relief or block or stop or prevent hydrochloric acid release. And that's why we said the prostaglandin have cytoprotective activity. They will block or they will prevent the release of gastric acid. And once that happens, then then the activity. So when that happens, when you block the histaminergic pathway, that means you will have a relief, and the person, of course, you have the cytoprotection, and that's why we did mention you do require the constitutive prostaglandin E cell is always constitutive, so that they offer the cytoprotection. Other epithelial cells in the mucosal lining, under the influence of the prostaglandin mediated pathway secretors, as I was mentioning, you can also secrete bicarbonate and mucus. So also you have other cells within them, the mucosal lining, again under the influence of the prostaglandins, can also secrete bicarbonate and mucus. Bicarbonate, sodium is always there. The bicarbonate is a base neutralizing the acid. The mucus acts as a plug. It blocks or it covers the ulcer, and both of which are important in protecting the gastric lining from the effects of the acid secretion. So this is like a physical. For the mucus, it's a physical barrier. Of course, the bicarbonate will neutralize the acid. Examples now: commonly prescribed anti-ulcer drugs, which are H2 receptor antagonists. That's what we are starting with. We have cimetidine, ranitidine, famotidine, nizatidine. There are others, but these are the four which are commonly prescribed, and they're the ones that we will concentrate on. Let us look at the historical development. And the historical development, the H2 blockers will start with histamine, because that is the endogenous compound that causes the release or triggers the secretion of hydrochloric acid. So you want to start your development from there. You do structural modification on the histamine to see whether you can get a molecule that will block that activity of histamine. And indeed, it started with guanyl histamine. Remember, it started with guanyl histamine, and guanyl histamine provided the lead. Extension of the side chain. So what I will do is that because we read this, we might not understand it very well. Let us go to the actual, and then we go back. Sorry. Where? What has happened? Yesterday. I can't move. Do what it did yesterday. Where's my arrow gone? Oh, where has the arrow gone now? How else can I move? She did yesterday also. Okay. Just don't know what had happened. All right, so we continue on. Without this arrow, you can't move. So I think that's where we were. I'll be using the lower one to move. I don't want to get there again. So many distractions. Oh my goodness, what's happening? So I want us first to look at the historical development. Yes, I want us to look at the historical development. First of all, we look at it, seeing the actual things that were being done so that we can be able to understand the notes. So we are saying, I think that is the next one. Right. So we are saying, of course, our endogenous compound is histamine. You can see that's the structure of histamine. So it was first converted to guanyl histamine. And for guanyl histamine, it means you add the guanidino moiety, which is this one here. So we added the guanidino moiety and it became guanyl histamine. And that compound was found to have very weak, it was a very weak antagonist. And it was the lead molecule. It had some weak antagonistic activity. It was considered to be the lead molecule. Now they started working on the guanyl histamine, and the first thing they did is increased the number of atoms on the side chain. So they did extension of the side chain. So you can see these are 1, 2. We are considering before you get to the terminal nitrogen. Don't forget, this was the terminal nitrogen of histamine. So here we have 2, they added 1. So there you have an extension of the side chain, and you have 3. And you can still see the guanidino moiety is still there. That compound was tested. It was still found to have antihistamine, H2 blocking activity. Then from there, they decided to change the guanidino moiety into a thiourea. You can see that is your NH, and that's your NH. If it is urea, this will be carbon double bond oxygen. So if you replace the oxygen with a sulfur, remember it was a guanidino before, if you go back, it was a guanidino moiety. So if you look at it here, this is an NH. So in place of that NH, guanidino moiety, they put an S, and that became a thiourea. So they changed with the thiourea, and when they did that, they have still retained one, and then they also did extension. So they did extension. We had 3. So now we have 1, 2, 3, 4. And they changed the guanidino moiety to a thiourea. Advantage of this thiourea is neutral, and the resultant compound was known as burimamide. The resultant compound was known, and it had no agonist activity, but it was not orally absorbed. So that drug could not be given orally, but it had the advantage that it did not have any agonist activity. So that was a very positive move. But unfortunately, of course, because of the thiourea, these compounds were also found to have some appreciable toxicity. So the next step they did, if you look at this, the next step is that they replaced one of the methylene groups, the second methylene group, with a sulfur. You can see side chain, and it's a replacement indeed. They removed one of the methylene groups and replaced it with the sulfur, because you can see a retention of the number of atoms. That's why I'm calling them atoms. You see between the terminal nitrogen and the aromatic side and the aromatic ring, there is 1, 2, 3, 4. The imidazole ring here and the terminal nitrogen, 1, 2, 3, 4. So it's indeed a replacement of the methylene group with a sulfur, and retention, of course, of the thiourea. You can see there. And then also, in addition, if you look at this compound properly, you will see in addition, it has a methyl group at position number 5. We start here, position 1, position 2, position 3, position 4, position 5. So 2 major changes have been done. There is an insertion or addition of a methyl substituent at position number 4. Remember, when we were looking at the histamine agonist, or when we're looking at histamine agonist, we did mention, or when we're looking at some of these I think it was a histamine agonist, we did mention if you put a methyl group, or if you put a group here which is electron donating, methyl groups, RK groups, are considered to be electron donors. So when you put an electron donor here, or a methyl substituent here, remember, a methyl substituent will push electrons into this aromatic ring, and once it pushes electrons into this aromatic ring, it will increase the basicity. It will increase the basicity, or the nucleophilicity of this nitrogen. Now, this nitrogen will be more nucleus loving. It will be more nucleus loving. It will be a stronger base, because you have pushed in electrons. And therefore, once you push in electrons, you increase the nucleophilicity, you increase the basicity of this nitrogen atom. That means you promote the teletautomer. You to promote the teletautomer, because if this hydrogen is highly basic, then it will bind its hydrogen more strongly, and therefore there is no way it can allow for the loss of that hydrogen to promote what we are calling the pi tautomer. So putting an electron donor there will promote the teletautomer, as I have said, by making this nitrogen more nucleophilic or more basic. So that is the first reason why we have a methyl group substituted at position 5 of the imidazole group, to increase the basicity of the tele-nitrogen, and increasing the basicity of the tele-nitrogen promote the formation or the existence of the teletautomer rather than the pi tautomer. So that's the first stage. Then, when you look at the side chain now, we have introduced a sulfur. What is a sulfur? A sulfur is an electron withdrawer. So on the side chain, you have put an electron withdrawer. The role of the electron withdrawer, the function of the electron withdrawer, is to pull electrons. So this sulfur will pull electrons out of this ring, and therefore, because this is the nitrogen which is closest, this nitrogen is going to be electron deficient. The lone pair of electrons, or what you call the pi electrons, which are supposed to be used in case it's forming a base, will be moved or will move along the side chain, and therefore that nitrogen will be less basic. That nitrogen will be less basic. You will have increased its pKa and decreased its Ka. It will be so you have, yes, you will have increased. You will, because when it becomes basic, you need to increase the K. You need to decrease the Ka. So if you decrease the Ka, you will increase the pKa. So you will increase the pKa. In increasing the pKa, so we have said it's becoming more, sorry, let's get it right again. It's becoming more acidic. If it is more acidic, it means it has a higher Ka and therefore a lower pKa. So we are decreasing the pKa, and in decreasing the pKa, you are decreasing its basicity. Once you decrease its basicity, that implies you do not allow this nitrogen to form the NH. Remember, we did mention that the imidazole ring at one time can undergo tautomerization, where either we have it as the teletautomer or the pi tautomer. So once you decrease the basicity of that group, once you decrease the basicity of this group, then you do not allow for the formation of the pi tautomer, and you have already, because of addition of the methyl group, promoted the formation of the teletautomer, and that is what you require. The teletautomer is what you require for binding the H2 receptor. We did mention, when look at H1 receptor, it really, the issue of tautomerization does not influence the molecule that binds the H1 receptor. But for H2 receptor, you require the teletautomer to be predominant, because it is the teletautomer that binds, teletautomer that binds the receptor. So I hope we are together there. That is very important for us to carry, or for us to understand, that the way those tautomers bind the H2 receptor is different, with the teletautomer binding the receptor better than the pi tautomer. Let me put my phone silent. It's becoming a nuisance.